Hello, geometry students. This is Mrs. Raposa. I will be presenting your hybrid out lesson on angle-angle similarity. Your notes might say 6.1 here, but it is actually section 6.3. That was a typo, so you can change that to 6.3. Your notes should look like these. If you don't have a copy, perhaps you can print out a copy, or you can just take notes on blank paper. Let's get started. By the end of this lesson, you should be able to find missing side lengths, missing perimeters, and missing areas of similar figures. And you should be able to prove whether two triangles are similar using the angle-angle similarity postulate. Last week in class, we learned about the side-side-side similarity postulate and the side-angle-side similarity postulate. The angle-angle similarity postulate tells us that if we see two angles in one triangle that are congruent to two angles in another triangle, then we know that those two triangles must be similar. So you can go ahead and jot that into your notes. For example 1, we're asked to determine if any of these three pairs of triangles are similar. If they are, write a similarity statement and explain how we know they're similar. At first glance, example 1a may look like we cannot use the angle-angle similarity postulate because I do not have two angles in one triangle congruent to two angles in the other triangle. However, it is always important that you find the missing angle measure if they're not all given before you come to any conclusions. So let's go ahead and do that. In any triangle, I know that the three interior angles have to add up to 180. And since this one is already 90 degrees, we've already used up 90 degrees, then I know that these two angles together, angle A and angle C, have to add up to 90 degrees. So the measure of angle A plus the measure of angle C is going to equal 90 degrees. And to find the measure of angle C now, all I'm going to do is I'm going to subtract 56 degrees from 90, and that will give me 34 degrees. So the measure of angle C is actually a 34-degree angle, meaning that it's congruent to angle F. So angle C is congruent to angle F, and I do have two angles in one triangle congruent to two angles in the other. I also know that the measure of angle A, which is 56 degrees, has to be the same measure as the measure of angle E. Because if two angles in one triangle are congruent to two angles in another, then the third angles must also be congruent. So I'll go ahead and write my similarity statement. I can see that angle A matches up with angle E, angle B matches up with angle D, and angle C matches up with angle F. So that means that we have triangle ABC similar to triangle EDF, and we know they're similar by the angle-angle similarity postulate. So let's go ahead to example 1b. I can see that I have two isosceles triangles, and I know that the angles across from the congruent sides have to be congruent. So I know that angle J has to be congruent to angle L. And I also know on this triangle that across from the two congruent sides are angles M and angle N that have to be congruent. So I'm going to go ahead and mark them congruent. And anytime we're considering using the angle-angle similarity postulate, I need to know all of the angle measures in both triangles. So let's do that. To find the measure of angle J and the measure of angle L, I'm going to subtract the 36-degree angle from 180 degrees to get 144. So these two angles have to add up to 144, and they're both the same measure, so just take 144 degrees and divide it exactly in half, divided by 2 to get 72 degrees. So angle J and angle L are both 72-degree angles. In triangle MNO, what I did was I added this 74-degree angle to this 74-degree angle to get 148. And to find the measure of angle O, just subtract the sum of these two, 148 from 180, to get that the measure of angle O is 32 degrees. And since there are not two angles in this triangle congruent to two angles in this triangle, I can say that these two triangles are not similar. So I'm going to go ahead and say that these two are not similar. And this one, it was similar. And we had that triangle ABC was similar to triangle EDF by the angle-angle postulate. Let's go on to example C. The first thing that I noticed with example C is that I have a pair of vertical angles. So I know that those two vertical angles have to be congruent. So I'll go ahead and mark them congruent. And since ST is parallel to QP, and this transversal creates alternate interior angles, I know those two alternate interior angles, angle P and angle S, also have to be congruent because those are alternate interior angles formed by two parallel lines in this transversal. I could also say that angle T is congruent to angle Q because they are alternate interior angles formed by two parallel lines in this transversal. But right now I have enough. I have enough to say that two angles in one triangle are congruent to two angles in another. So therefore, these two triangles have to be similar. I know that angle P corresponds to angle S. I know that angle Q corresponds to angle T, and I know that the two vertical angles correspond with each other, represented by vertex R. So I can say triangle PQR is similar to triangle STR using the angle-angle similarity postulate. Done with that one. Now it's time for you to try one of these on your own. You want to determine if this triangle is similar to this one, and if it is, to write a similarity statement. I'm going to have you start by finding the measure of angle DFE. Then you can find the measure of angle CDF. And then determine if the triangles are similar. For example 2, we're going to find the ratio of the side lengths of these two rectangles, and we're going to find the ratio of perimeters, and we're going to find the ratio of the areas. This was a typo. You can cross that off. So let's go ahead and do that. To solve for x, we'll set up that 8 relates to x the way that 12 relates to 9. So 8 is to x as 12 is to 9, because those two sides correspond and these two sides correspond. So now to solve for x, all I'm going to do is say that 8 times 9 is equal to 12 times x. That will give me 72 equals 12x. And when you divide each side of this equation by 12, we get that x is equal to 6. So I'm going to go ahead and mark this side of the rectangle with a side length of 6. Now, to find the ratio of sides, all I have to do is compare one figure to the other. I'm going to go bigger rectangle to smaller rectangle, and that will give me an 8:6 ratio, which reduces to 4/3. So the ratio of sides then is 4:3. I could also write it this way if I wanted to, 4:3 ratio. You may recall that the ratio of perimeters is the same thing as the ratio of sides. I'm going to go ahead and write that down for now. And we'll compare the ratio of the perimeters. Okay, just to verify that the perimeter of the rectangles are in a 4:3 ratio, we can calculate the perimeter of this rectangle. That'll be 2 times 12 plus 2 times 8, and that will give me a perimeter of 40. And the perimeter of this rectangle will be 9 plus 6 plus another 9 plus 6, so 2 sets of 9 plus 2 sets of 6, which is 30. And so the ratio of the perimeters then would be a 40/30 ratio. And 40/30 definitely reduces to 4/3. So the ratio of the perimeters is indeed the same thing as the ratio of the sides. The ratio of the areas, that's a little different. Let's take a look at that. Okay, now let's see how the areas compare. They don't compare the same way that perimeters or sides compare, but there is a relationship between this ratio and the ratio of areas. Well, the area of any rectangle is length times width, So the area of the larger rectangle will be 12 times 8, which is 96. And the area of the smaller rectangle will be 9 times 6, which is 54. So then that means that the ratio of the areas of these two rectangles will be 96 to 54. And both 96 and 54 are divisible by 6. So this ratio, when you divide each the numerator and denominator by 6, reduces to 16 over 9. So there's a 16 to 9 ratio, not the same as the ratio of sides or ratio of perimeters. However, it is the ratio of sides squared. So if we square both the 4 and the 3, we'll get the ratio of the areas. And that makes sense because for every 4 units on the side here, there's 3 units here. So that means for every 4 by 4 square here, I'm going to have a 3 by 3 square here. So for every 4 by 4 or 16 square units on this figure, I'll have a 3 by 3 square or 9 square units on the smaller figure. So then let's use purple to, there we go. And we are going to say that if the ratio of the side lengths is A to B, then the ratio of the perimeters will also be A to B. It doesn't change. It's the same thing. However, to get the ratio of areas, I square both the numerator and the denominator. So that will give me A squared over B squared. Let's use that to do a few problems. Let's do example 3. And to do example 3, it might be helpful if you had some different colored highlighters, pencils, or pens to mark up the corresponding parts of this figure in the same colors. Try not to use markers or anything that'll bleed through the paper though. So if you need to stop the video while you find some colors, go ahead and do that. Remember that this similarity statement is the key to knowing which pieces correspond. So the first 2 letters here correspond to the first 2 letters here. So AB corresponds to PQ, and I'm going to go ahead and mark those in one color. Blue. AB corresponds to PQ. And I can see that side BC is going to correspond to side QR, second and third letters. I'll do those in a different color. Let's do green. So BC corresponds to QP. And the third and fourth letters, CD, correspond to RS. Let's use red. And I can see here that side RS is congruent to side TP. So RS congruent to TP, that's the third and fourth letters congruent to the side with the last and first. So I know that CD, third and fourth letters, is going to be congruent to EA right here. So I'm going to go ahead and mark that congruent, that this is the same length as this piece. So I know that right away that this is 12 because this piece is 12. So that means that I've already found one of the lengths that I was asked to find, CD. So I'll go ahead and put down that CD has length 12. Let's find lengths BC first. So BC corresponds to RQ the same way that AB corresponds to QP. So that means that BC is to 4.8 as AB, which is 10, is to QP, which is 8. So I'll have 8 times BC is going to equal 10 times 4.8, which is 48. And just divide each side of the equation by 8, and you'll get that BC has a length of 6. So nice. I'll go ahead and fill that in over here. BC has length 6. Now let's find length RS. Well, I know that 10 is to 8, I can actually reduce that. Instead of saying the ratio of sides is 10 to 8, let me put that over here. Let's make my life a little easier and reduce that to 5 to 4. If I had said BC is to 4.8 as 5 is to 4, I still would have gotten the answer 6. So I'm just going to keep using this ratio. So the ratio of sides is 5 to 4. So that'll be, again, AB is to QP as CD is to RS. So that will give me 10 to 8 ratio over here, which is the same thing as a 5 to 4 ratio. I can use 10 to 8 if I want to. It'll give me the same exact answer, which is 12 to RS. And when I solve that proportion, I'm going to have 12 times 4, which is 48, is going to equal 5 times the length RS. And all I need to do now is divide each side by 5, and 48 divided by 5 is going to be 9.6. So RS has a length of 9.6. And I'll go ahead and mark that over here too. Remember that we said that the ratio of sides is the same as the ratio of perimeters. So I'm just going to say that the ratio of perimeters is also a 5 to 4 ratio. And that will help me to find the missing perimeter here, because I know that 5 relates to 4 the same way that this perimeter relates to this perimeter. So I'm going to go ahead and solve for the perimeter. Let me do it in blue for the perimeters. So I'll say that the perimeter of this, the ratio of perimeters 5 to 4 is equal to this perimeter 45 to the missing perimeter. Again, I'm going bigger figure to smaller figure for the ratio of perimeters, so bigger figure to smaller figure for the two perimeters. That will give me 5 times P is equal to 45 times 4, which is going to give me 180. And to just divide each side by 5, and 180 divided by 5 will give me 36. So the perimeter of the smaller figure then, PQRST, is 36. Now let's find the missing area and the ratio of areas. Remember we said that the ratio of areas is going to be the ratio of perimeters just squared. So square both numbers. So I'm going to square the 5 and I'm going to square the 4, and that will give me a ratio of 5 squared. I'm going to put it down here where it came from too, so you'll know it's 5 squared to 4 squared. And that'll give me a ratio of 25 to 16. Makes sense? For every 5 units on a side, I have 4 units on a side here. So every 5 by 5 square, I'll have a 4 by 4 square here. So for every 25 square units in this figure, I'll have 16 square units on this one. Remember, area is measured in square units, and it makes sense to square the side lengths, the ratios. So let's go ahead and solve. So I know that the ratio of areas is 25 to 16. So 25 will relate to 16 the same way that this area relates to this area. So I'll go ahead and do that down here. So 25 is to 16, the same way that the area of the bigger figure, 100, is to the area of the smaller figure. I'll just call it A. Remember, I did bigger figure to smaller figure to smaller figure for this ratio, for this proportion, for this ratio too. So that'll give me 25 times A is equal to 16 times 100, which is 1600. And all I have to do now is to divide each side of the equation by 25, and that will give me 1600 divided by 25 is 64. You can go to your calculator and check it out, but That is the area. 1600 divided by 25. So I know that the area of PQRST is 64, and area is measured in square units. I'll go ahead and just put units squared, whereas this one would be in just linear units. And we've done example 3. Our last example is example 4. If it says example 3 here, just cross out, put 4 in its place. I think this was corrected before the handouts went out. So in this diagram here, we're told that BC is parallel to ED. So go ahead and mark them with arrows to indicate that they're parallel. And we're told that ED equals 12 and BC equals 20. So go ahead and mark that too, please. Whenever I have one triangle inside another, I like to draw them separately. It helps a little bit. I know that in both of these angles, that angle A is obviously going to be congruent to itself. So, because this angle in both triangles comes from this angle. And I know that since these two lines are parallel, and this line is a transversal that cuts those two parallel lines, then these two corresponding angles also have to be congruent. So angle D in triangle ADE is congruent to angle C in triangle ACB. So by the angle-angle similarity postulate, I can go ahead and say that these two triangles are similar. So let's go ahead and mark that. How do we know the triangles are similar? They're similar by the angle-angle similarity postulate. And let's write a similarity statement. I know that triangle ADE is going to be similar to triangle ACB. So that would be one of the correct similarity statements that we could write. And let's write down what the ratio of sides is, small triangle to the big triangle. So small triangle to the big triangle, the ratio of sides is 12 to 20. And so I'll write that over here, 12 to 20, which is going to reduce to a 6 to 10 or 3 to 5 ratio. So we have a 3 to 5 ratio for the ratio of side lengths. Now that means that the same thing is going to be the ratio of perimeters. So the ratio of perimeters will be the same, 3 to 5. So now let's use this ratio to find the perimeter of triangle AED if I know that the perimeter of triangle ABC is 60. Notice that I do not need to know what the other two side lengths are in order to find the perimeter of this triangle. All I need is this ratio and the perimeter of the figure to which it's similar. So I have the perimeter of triangle ABC, which is the larger one, so I'm going to write that here, that this is the larger figure's perimeter. And I think it's a good idea to do it when you're asked to find the perimeters of similar figures. And AED is the smaller one, so I'll put that that's the smaller one. The reason why it's important to write that down here is because when I write my ratio, which number's on top is going to matter. If I write a 3 to 5 ratio, then I'm comparing the smaller figure on top to the larger figure in the denominator. So I'll say this ratio, 3 is to 5, the same way as the perimeter of the small figure, which is unknown, so I'll put P, is to the perimeter of the larger figure, 60. A common error is for students to put 3 to 5 over here and then put 60 over P on this side. But remember, if I put 60 over P, then I'm doing large to small when I set this up as small to large. So they have to be set up the same way. So now that I have it set up, I'll know that 3 times 60, which is 180, will equal 5 times P. And now all I have to do to solve for P is to divide each side by 5. And 180 divided by 5 will give me 36. So that means that the perimeter of triangle AED is 36 units. Now we're asked to find the ratio of areas, small figure to big figure. Remember that the ratio of areas is just the ratio of sides, 3 to 5, right here. Circle it. Squared. So I'm going to take 3 and square it, and the 5 and square it. So the ratio of areas then will be 3 squared, or 9 to 5 squared, which is 25. So there's a 9 to 25 ratio for the ratio of areas. Let's use that to find the area of the bigger figure, triangle ABC, if we know the area of the smaller one. So again, I'm going to go ahead and write up here that this is the area of the smaller figure. So I'll know which one goes on top and which one goes on the bottom of the fraction. And this is the area of the larger figure. So when I set up my ratio, 9 to 25, because that's my ratio of areas, I have the smaller figure's area on top. And the smaller figure's area is 79.2. And the area of the larger figure is what I don't know, so I'll give it the variable a for area. And then I'll do 9 times a and set that equal to 79.2 times 25, which gives me 1,980. And now, to get a, all I have to do is divide each side of the equation by 9. So divide this by 9, I get a. Divide 1,980 by 9, and I get 220. So the area of the larger figure, ABC, is going to be 220 square units. And now you are done with example 4. On the back, you'll find a problem that you're to try on your own. You're told that figure ABCDE is similar to figure PQRST. And the first question, what is the ratio of sides, comparing the bigger figure to the small figure? Remember to reduce your ratio. And for question B, what will be the ratio of the perimeters then, now that you know the ratio of sides? And question C, once you know the ratio of sides, it's very easy to use that to get the ratio of areas. What will be the ratio of areas? And for question 3, you're told that the perimeter of figure ABCDE is 30, and you're asked to find the perimeter of figure PQRST. Remember, you don't need to know all the side lengths to find the perimeter here. All you need is the ratio of perimeters and the perimeter of the other figure. Make sure you show your work here. And last but not least, question 4. If the area of figure ABCDE is 60, find the area of PQRST.